Okay. Hey, who have I got? Who? Okay. So, yesterday we saw about turning force. Two supports, yeah. So we're going to continue with that. Okay. I'm going to do more examples for you, different types of turning force problems. Okay, so we'll say this is 10 kilograms, and there's a rope here. Okay, so there's a weight here, 10 feet, and the distances. This is 3 meters, and then this is 4 meters. Okay. Now, what we have here is we have like maybe like a pole or a bridge or something, and it's held up by one rope. Okay, and we want to know that this is called the tension. Tension is the force in the rope. We want the force here. Now it looks like I drew all my forces, doesn't it? But there's one force missing. Can you see what that force is? What did I not draw? I have tension, yeah, that's tension there. So that's the tension force. What else am I missing? What other force? Do I have all my forces on the bridge? The wall, yeah. Because the wall is pushing against the pole. I'll just call this a pole. The wall is pushing against it, okay? Because if the wall wasn't there, the pole would go to the left. But the pole doesn't go to the left, so it means the wall is pushing back. So my next question to you is, which way should I draw this force? I have many choices here. What way should I draw it? What do you think?
Down.
Down maybe? What do you think? Up, right? Yes?
Up.
Up, yeah.
And in the wall and up. Or down or in the wall.
You're close, you're close. It's actually not, it's up and right. It's actually like this. Now why is it like this? Why is it not like this? Because you think maybe it should be like this. Well, the reason is, if you think about it, if you look here, if I push straight against the wall, I don't move because the wall is pushing back straight, okay? But if I don't know, if I put my hand down lower, okay, I'm not falling down because it's holding me up. So it's also pushing out, but also pushing up. It's giving me support. Like, it's hard to do here, but this would be straight. But then if I put my hand down here, well, I know this is here, but if I put my hand down here, it's not straight, because I can feel that if I move my hands I fall down. So it's also pushing up as well. And in fact, it's the friction on the wall, because if this wall was ice and I put my hand on it at an angle, what would happen? It would slip, wouldn't it? Yeah. So it's actually the friction as well that's keeping it going up. Okay, so let's call this force here we'll call this force reaction or, and this angle here, I don't know it, I'll call it theta. Yep. Okay. Do you know where Young is? No? Well, that clock is fast. Anyways, let's have a look at how to do this. So, do I know this angle here? Okay, just to be clear, this is the information you would get in the question. So now, I'm going to do the answer. And what I want to know in this question is, what is the tension force in the rope? What is the reaction force by the wall? And what is the angle of this force by the wall? These are the three things I want. Okay, so let's have a look at doing that. Okay, first question. Can I know this angle here? Well, I can, because I know that tan alpha equals 4 over 3, because it's a 4-3 triangle. So tan alpha is 4 over 3. So alpha is tan inverse 4 over 3. Can you tell me this, please, on your calculator? Point. Now let's break our tension up. So I'll draw it in here in blue again. This force here, that would be T cos alpha. And then what's this one here? T sine alpha. So I'm just going to draw this again. It's getting a little bit messy. And also this one here, that's or cos theta. And then this one here, that's or sine theta. Now I'm just going to draw this again. So I'm going to go down. So if I go down, okay. So here is, what do we say, tangent. Here is or cos theta. Here is or sine theta. And then here is T cos alpha. Can you type in cos that angle you got? It should be 0.6. Yeah, so that's 0.6t. Let me write that a bit clearer. 0.6t. And then if you do t sine that angle, you get 0.8. You should. Yeah. Do you see how I got the 0.6 and the 0.8? They came from cos alpha, and I know the alpha. That's how I got it. Now when you look at this doesn't look as difficult now, does it? It actually looks much easier to do once you've done it like this. Do you remember the verb for when you take your vector and change it into an x and a y? Remember that verb? Anybody remember it? Anybody? That verb? Verb? Nobody? Oh, okay. Louise, Saeed, do you remember this verb? When you take a vector and change it into the x and the y? No, magnitude is the name of this part. Oh, we forgot. Oh, not resultant, no, the other one. Resolve. So resolve is when you take a vector and break it into x and y, and then what you said, resultant, is the opposite. Resultant is when you take a vector in x and y and add it together. Vocabulary? Yes, okay. Right, so we have here or sine theta plus 0.8 equals 98.1. That's the 10G, if you're wondering how I got that. It's 98.1 newtons. Okay? That's great.
This
Yeah?
0.8,
Yeah. It's the sine one. If you type in sine this angle, you get it. Yeah. Come in. Oh, you're so late. Why are you so late? Yes? What about the bus? Tell me more. Why are you late? What's wrong with the bus? Sit down. Go. Be careful. Go under, okay. Right. What was I saying? You asked me a question, Saeed. It's okay now?
Yeah.
Okay. So then the next thing we need to do is get the turning force. So I will take this point here is the turning point. What's this distance? Well, if I go back, it is 1.5 meters. And then what's this whole distance? 3. Okay. This one, clockwise or anti-clockwise? No.
Which one?
This one? No.
No.
Nothing. Yeah, because it goes through the point. This one?
Anti.
No.
Clockwise.
No. Nothing, because it goes through the point. Right, this one. Clockwise. Yes. This one? Nope.
Nothing.
Nothing. Yeah. And then this one here?
Anti-clockwise.
Anti-clockwise. So this clockwise one here must equal this anti-clockwise one here, like we did yesterday. So we get now 1.5 times 10G must equal 3 times 0.8G T. Now this is really, really good. Because what can I get from this one here? What can I get?
T.
Yes, I can get T, can't I? So that's really good. That makes me happy. So can you give me T, please? So we're happy, mostly. Yes? Now, there's a problem here. How many things are in this one? I don't know. How many unknowns?
2 unknowns.
Well, yeah, now it's 2. It was 3, wasn't it? So we don't know or, and we don't know theta. So, if we have 2 things we don't know, we must have 2 equations. But I only have 1 equation because I use this. I use this to get my t. So there's 1 equation I can still make. And I can still make 1 more, and that is or cos theta equals 0.6t. Why?
Because they're horizontal.
The horizontal cancels also. So what I'll do is I'll just write these 2 again. Hugo, I got your message. Why, what happened exactly? Okay. Get step over carefully. Easy does it. Alright. So I'll just write these again. Or cos theta equals 0.6t. And the other one is or sine theta plus 0.8t equals 98.1. And now we want to solve this. Now, the good news the good news is I know what the t is, don't I? So on your calculator, can you take this value for t and put it in here and put it in here and tell me what numbers you get? So I have now or cos theta equals
36.79.
and here or sine theta equals
49.04.
now can you take that number and bring it over here as a minus so we can do 98.1 minus that number
49.052.
49.052 newtons as well. I don't need to write them right now. Now we can't use elimination or matrix method. There's a special way to solve this type of problem here. I'll show you what to do now. So what we do, and can I scroll down? Yeah. Yes?
Thank you.
Okay, so we have or sine theta equals 49.05, and we have or cos theta equals 36.79. And the trick here, this is the trick, we can divide, okay, so elimination we can add or subtract, but we also can multiply or divide. So we can divide these two equations, or divide or, sine divide cos, 49 divide 36. So that's good because then they cancel. So I'm left with sine theta over cos theta equals, and can I have this number please? 1.34. Yeah, okay. Now there's a rule here, and don't worry, we'll do this in maths class. It's, so don't worry right now, but the rule here is when you have a sine and you divide it by a cos, that's the same as tan. And like I said, don't worry, we'll do that in maths class, okay? So now I get tan theta equals 1.34. So theta equals tan inverse 1.34. And what's that please? 33.13. 53.13 degrees. Now I'm nearly finished. The last thing to get is the or. So if I just look up for a moment, I will use, for example, this one here to get the or. Or sine theta equals 49.5. I have or sine theta equals 49.05. So that means or equals 49.05 over sine theta, which is 53.13. So my or is 61.3 newtons. So I have my answers. What was my answer for tension earlier? What did I get for tension?
61.3.
61.31. Yeah, okay, newtons. My or 61.3 newtons, and my theta was 53.13 degrees. Okay. I think it's only an accident that these numbers look similar by accident. I don't think it'll always, no, it shouldn't always be like this. It's just by accident. Okay, I'll do another problem now. I'll just give you a minute to write this down. Okay. Nearly there, okay. So it's not very different, is it? It's very similar to what we did yesterday. It's just longer, more equations, a little more complicated. But the ideas are the same. Okay, let's have a look at another example, yeah? Okay. So my next example. You got that, Saeed? Yeah? Or no? You need to write it down? Yeah. I can go down? Okay. Right, so let's have a look at this problem now. So this is a wall and ground, and then we have this time a ladder against the wall. And we'll make the ladder, I like easy numbers, we'll make it a 10 kilogram ladder here. And we'll put a person on the top, and we'll make the person a 100 kilogram person. And what else will we say? I need to tell you how long the ladder is, so we'll say it is a 6 meter ladder, 6 meters in length. Okay, what else did I tell you? I should tell you as well, that's 6 meters. I should tell you how big this distance here is. Let's say it's 1 meter from here to here. Okay. And I should tell you where the man is. So we'll say the man is, we'll say he's 1 meter from the top of the ladder. Yeah. He's 1 meter. Now, this is something I know is difference with the physics here and the applied maths that you did. In the exam, they don't make it clear, but I'm going to make it clear. I'm going to say the ladder is at the point of tipping. You're familiar with this expression?
Tipping.
Yeah. Now, what would you say then?
Every time we see just, then we just assume that's about to slip.
Okay, we'll keep it simple then. The ladder is just about to slip, but does not.
Maybe we just assume as soon as we see just and just
Yeah.
the point.
So what I'm saying here is all the forces cancel, just about, but they all cancel. So it's all balanced, just about balanced. And the other thing I'll say on this picture here, on this wall there is, to make it easier, which is what they normally do in the exam as well, there's no friction here, but there is friction here. Yeah. So that means we think about this wall as being like ice. Do you remember my example earlier? So it's slippy. So it means that the reaction here is straight out. that it's not at an angle because it's a slippy wall. It just is straight. You can't hold yourself on the wall up or down. It just pushes out. Okay? But the ground has friction. Now, what way would I draw the reaction here? Left, right, up, at an angle? What do we think? What do we think? Which way should I draw the reaction here?
Right.
Like this way? Yeah? Any other ideas? Let's see what everybody thinks. So far we think this. Anything else?
I'd say the opposite way.
This way?
We going that way, so the reaction should be the opposite direction.
Yeah, maybe. Or maybe down, yeah, or maybe up. It's go like this.
Yeah.
And again, it's at an angle. Because it has two parts. The first part here is stopping the ladder from slipping. And the second part here, going up, is the ground pushing up. Stop the ladder from falling down to the centre of the earth. So just like in the last example, oh yeah, I should put in the man is here as well. That's 100G, and then here the ladder as well. That's a 10G. So I'll draw this again, like in the last one, a bit clearer. Okay, can I draw it again? Yeah. All right. So let's just keep it a bit simpler, the picture. So here there's S cos theta, and then here S sine theta, and then here there's an or, and then here in the middle there's a 10G, which is 98.1, and then up here is the man, and he's a 100G, so he's a 981 Newton force. We also know some distances. I know that here to here is 1, and then here to here is 3, and then the total is 6. The ladder is 10G. No, 6 meters long is what I was saying.
Oh, sorry.
Yeah. Now, we can actually know the theta here, because if I go back to my picture up the top, look here, this triangle, this is 6 meters, and how big is this? 1 meter. We can use Pythagoras to get this piece here. We'll call it x. Pythagoras, 1 squared plus x squared equals 6 squared. You know Pythagoras? Yeah? You know Pythagoras, his name?
Yeah.
What's the Chinese for Pythagoras? Go-go-dee or something like this? What is it?
Go-go-dee.
Yeah, that's it, yes. You know this person? Or maybe this is not translation well. I think I said this before, but really quick here, Louise. When you have a triangle, and this is ABC, we have a squared plus b squared equals c squared. It's called Pythagoras, or Gogodini. Yeah. It's still Pythagoras in Arabic, I know. Yes, yes. So anyways, can we use our calculators and we get x equals the square root of 35. What's that, please, as the decimal?
5.91.
5.91? Okay. 5.91 meters. So this theta here, I can say tan theta equals 5.91 over 1. So then what's theta equal to? If we do tan inverse, 80.4 degrees. Okay, so I'll go down back to my next diagram. Okay, so here, Ugo, can you type in sine of 80.4 and can you type in Ibrahim cos of 80.4? So Ugo, what did you get? You can give it to me as a decimal.
Yeah. 985, well, 986.
S. Okay, and then what did you get for the cos one?
0.16.
16, what's next?
6.
0.166.
Yeah.
Yes. Good. Good. So I don't need to write this theta in anymore for the moment anyways. Okay, let's see what equations we can make. So I can say 0.986s equals 98.1 plus 981. This one here is saying that the up force equals the down force. So there's only one force going up, but there are two forces going down. Now what force is going to the left? What's going to the left? 0.166s. And what's going to the right? Just the one force, isn't there? Or. That's right, isn't it? Left and right. So this is left equals right. Yeah? Oh wait, no. No. I just realized I did something wrong. Something very bad. Ah, sorry. I'm sorry, I'm not thinking. This angle here is not the same as this angle here. See this 80.4? That's for the ladder. This angle here for the reaction is not the same. So in other words, my problem is here. Rats. I don't know these parts. I'll just undo. It's easier for me to do this, I know. Sorry. Terrible. S cos theta, and then here S sine theta. Now I'll give you a minute to fix your notes, but sorry, my problem here is this is not theta. I shouldn't have drawn this in. I'll let you fix this. I'll give you a minute. I knew I was making a mistake because I saw that the question was going to be very easy, and I know that they're not very easy. So I thought something went wrong. It was becoming too easy. Okay, but your answer of 80.91, that's still good, but that's the answer for this big angle here, okay? That's 80.4 degrees. Not for the theta. So I'll say that again, sorry for the confusion. It's 80.4 is for the ladder and the ground. The theta is smaller than this, or maybe bigger, I don't know, but it's not 80.4. Okay, now we can start. So same ideas. S cos theta equals or, and S sine theta equals 981 plus 98.1. Can you add these two together, please? The 981 plus 98.1.
1079. Point one.
1079.1. Okay. And that's for S sine theta. Now, do you see the small little problem? I have, how many things do I not know? 3. So I need one more equation. What equation have I not used yet? I've done up equals down, left equals right. So what's left? Yes? Sleepy morning? Yeah. This one here, left equals right. This one here, up equals down. So what's left? There's one left. Turning force. Clockwise equals anti-clockwise. Where would you like me to put the turning point? Where do you think would be a good place for the turning point? Up here? Down here? In the middle? What do you think? Up here?
Yeah.
I think down here. Now the reason I picked down here is because then this one goes. This one goes as well. This one here, clockwise or anti-clockwise? Anti-clockwise, if we picture. Going, yeah, anti-clockwise, going around this way. What about this one? Anti-clockwise. And then what about this one? Clockwise. So this one here must equal these two. What's this one? It's nothing. And this one here? Nothing. Okay. So we have now the clockwise one equals these two anti-clockwise ones. But the problem is I don't know the distance. So I need to draw the triangle again. I'll do it on the side. But the triangle on the side is just for the distances, okay? So I'll just draw it on the side here. I know that this here is 6, 1, and what was this one here? 5.91. I know this angle, what's this angle? It's 80.4. And I know this is in the middle. Now that's really, really good, because if this is in the middle, and this is going down, how big is this distance? It's exactly 0.5, you're right, because the total distance is 1 meter for the whole lot. So that means this piece here is 0.5. Why did I not use this distance? Why am I using this distance? Why did I not use this distance?
This is still on the triangle that you want.
No, not quite that. Why do I use this distance, not this distance? Because
Are we sure it's 30? That's not.
yeah, but my question is, this turning force is force multiplied distance, so why do I not use this distance? Why do I use this distance? Thank you, Who. Yes. This one is the perpendicular distance, not this one. It's not perpendicular. So we always use the distance that's perpendicular. Remember perpendicular distance? Yeah. Now, there's a force here going down, as you know. So now I need to get this distance here. Okay. We know this angle, 80.4, and we know this distance here. How much is this distance? 1. So yeah, so this distance then is 5. So I draw that triangle here on the side. That's 5. This we don't know, and this angle here, 80.4. I can say cos 80.4 equals x over 5. So what does x equal? 5 cos 80.4. But you knew that, because if you have this triangle, and this piece is 5, and this piece is 80, is this cos or sine? This is cos. This is 5 cos 80.4. What's that on your calculator, please?
0.83.
0.83. So that's this distance here up to here is 0.83. So I can go back now. And now we can do our turning force. Okay. First one, what's this distance here? What did we say this distance here was?
0.5.
Yeah, so 0.5 multiplying 98.1 plus, what's the distance to the next one? 0.83 was it?
Yeah.
Yeah, times 981. That must equal anti-clock. So look here, here's the force going this way. So I must use this distance because it's perpendicular. What's this distance? Not 6, no, it's
5.91.
5.91, is it? So 5.91 multiply or. Okay, Ugo, or sorry, no, Ibrahim, do you mind adding these two together? What do you get?
866.
No, divided by 5.91, and we have the or.
146.06.
0.7 degrees, okay. Sorry, degrees, sorry. Oh man. Newtons, yes, thank you. Now that I have or, I can put that back into this one here. So now I have S cos theta equals 146.07, and then I have here S sine theta equals 1079.1. And I do my same trick. What's my trick here? What should I do? Divide. So divide, cancel, cancel. Sine divide cos, what's that? Tan, yep. And Ibrahim again, sorry, do you mind giving me this division? Should be around about 6 or something. Okay, so now we can get the theta is 82.29 degrees. Okay, so we have theta, we have or, where's my or gone? We have or, so what's left? S. So I can use this to get the S. I have S equals or over cos theta, which equals 146.07 over cos 82.29. Okay, so what's the S now?
$1,088.78.
1,088. Okay. Right, so I got my S, got my theta, and I've got, what else was I looking for? The or, which is here. I have all the three. I have the two reaction forces and the angle as well for the reaction force on the ground. So, once you have that written down, I just want to recap. Do you have that? Nearly, okay. Yep. Okay, so I know these are quite long, but there's just a few simple ideas that we're using. So the ideas are that the up force equals the down force, the force to the left equals the force to the right, and the force going clockwise, turning force, equals the turning force going anti-clockwise. And there's a word here that describes this situation, which I actually haven't given to you yet. Equilibrium, and is there anything else? Oh yeah, there's two other words I need to show you. Equilibrium. So if something is in equilibrium, it means all the forces are balanced. That's what equilibrium means. Yes? Got that word, equilibrium? Yeah. Okay, so there's one more word I want to deal with you that's a new word. Okay. Can I go down? Yeah? Yeah? Okay, so there's a very special type of turning force problem. And if you give me your bottle, yeah. So if you look here, when I open the lid, when I turn it, okay, this is a special type of problem. What's happening is I have a force going this way and a force going this way. Now, if you add these together, what happens? You cancel them, yeah? So the lid does not move up or down or left and right, because there's no left or right, and the up and the down, they cancel. But what does happen is it turns. So this is called a couple. When you have two forces like this, and the only job they do is to make something turn. And this here is the radius, and this here is the radius. This turning force, this one here, clockwise or anti-clockwise? Anti-clockwise. Anti-clockwise, yes. Or F. And this one here? Anti-clockwise as well. Plus or F. So in total, 2 or F. Is there any anti-clockwise force? No. It's only clockwise, and the reason there's no anti-clockwise is because it's not in equilibrium, it's not balanced. What is it doing? It's rotating. Okay? So this is called a couple. And you can see here the formula is quite simple, 2 or F. But what's 2 or? There's a word for 2 or. What's this called? What's it called? Yes? Diameter. D. Diameter. Diameter. So you can also write the formula as just diameter multiplied force.
Clockwise or anti?
This one is, oh sorry, yeah, I wrote clockwise, thank you Saeed, anti-clockwise. Oh yes, I see some people have trouble spelling clockwise and anti-clockwise, so let me help you. This is clockwise, and then this is anti-clockwise. And if you are in America, Americans don't say anti-clockwise. Does anyone know what Americans say? No. Keep it simple. No, not weird. No, there's another word for anti-clockwise? No. Counter-clockwise. What they say in US of A. Counterclockwise. So if you have if you're watching an American lesson online or an American web page or a book or something, they might say counterclockwise. I think counterclockwise is a better word for it than anti-clockwise. Because my wife's American and she says if you say anti-clockwise, anti makes it sound like you're against clockwise, that you're not in favour of it. So, yeah, but anti is very much you're against something, like anti-smoking. I think of words like anti-smoking. What does anti-smoking mean? You think smoking is a bad idea, yeah? No, anti-smoking.
Yeah, no, but what counts is smoking?
Well, counter-smoking doesn't mean the same thing, but anti-smoking means you're against smoking, Anti-drinking, anti-fast food, anti-whatever, means you're against it. So it seems funny to use the word anti here because it doesn't mean you're against clocks, right? You have no problem with clocks, do you? No. So really, it should really be counter-clockwise, because counter means the other way. But here in Europe, we say anti here, but I feel that the American word counter-clockwise is probably more accurate description of what it is, okay? So I should really use counter-clockwise, but most people here in Ireland and the UK would say anti-clockwise. Okay? Now, yes, if you look at your next page, there are 4 questions on the next page, and of course there were 4 questions from yesterday as well. Ibrahim, how many did you do from yesterday? How many did you get done? Yeah, okay, fine, yeah. You got, that's right, you and Nugo got the 4 done. And Louise? You got the first one done. I think Saeed, you're the same, are you?
Yeah, I tried to do, but...
you got stuck? 2.
Yeah.
Yes, okay, yeah. And Young, you did 2, okay. And you got them finished. Okay, so you still have 2 to do from yesterday, and then there's 4 from today. You should really try and have these finished today, because tomorrow's the tutorial, okay? So what I'd like you to do is, you should get number 1 and number 2 done today now, on the next page. And then, if you want, you can go back to yesterday and try and finish those if you want, okay? But if you look at the last page, number 1, you see number 1 on the last page? And number 2, they're just like the examples I did. So it shouldn't give you too much trouble. And number 3 is not so difficult, but number 4 is quite difficult. So I don't know you can try to do number 4, but it is quite difficult looking. Maybe it looks more difficult than it is. Yeah, it does look difficult, doesn't it? Okay, so you can work on this for about half an hour. I think half an hour should be enough time to get most of it done. And tomorrow, please try to have them all finished for tomorrow, and we'll look at problems in the tutorial then. Okay? Alright.